The M4 Sherman rolled off American assembly lines faster than any tank in history, 50,000 of them between 1942 and 1945. Detroit, Cleveland, and Chicago pumped them out like clockwork. But there was a problem that military brass didn't advertise in their production newsreels. The welds holding the hull plates together had a fatal flaw, and American tank crews knew it the moment they faced German guns in North Africa and Italy. Tankers gave the Sherman a nickname that still haunts military historians: Ronson. The same as the cigarette lighter company, whose advertising slogan promised, "Lights first time every time." Dark humor, sure. But when you're sitting in a 30-ton steel box that can transform into a crematorium in seconds, you find ways to cope. The British had their own term, Tommy Cooker. Neither nickname appeared in official Army reports. But scan through enough letters home from the front and you'll find them everywhere, written in the desperate scroll of men who'd watched friends burn. Here's what made the Sherman's vulnerability so maddening. It wasn't just the armor thickness everyone talks about. That was part of it. Yes, but the real killer was how the armor plates were joined together. The Army's standardized welding specifications, developed in 1941 and rolled out to every defense contractor in America, called for a particular type of butt weld, two thick plates meeting edge to edge with molten metal fused between them. Efficient, fast, perfect for mass production. Except when a German 88mm shell hit those weld seams at the right angle, something catastrophic happened that the engineers at Aberdeen Proving Ground somehow missed during testing. The weld would fail before the armor plate itself. The impact would crack the joint wide open, and the shell wouldn't even need to penetrate all the way through. The separated seam created a gap that let in superheated gas and molten metal fragments, enough to ignite ammunition, hydraulic fluid, or the fuel tanks. Crews had about 90 seconds to bail out once a fire started, and that's if the hatches weren't jammed and nobody was wounded. After-action reports from the Battle of Kasserine Pass in February 1943 showed something disturbing. Shermans were brewing up from hits that should have been survivable. Shells striking the lower hull sides, right where the belly plate welded to the sponson, were causing total losses. Crews who made it out reported the same thing. The tank didn't just catch fire, it came apart at the seams. Commanders requested armor upgrades. They got sandbags. They requested better guns. They got white phosphorus shells and instructions to flank the enemy. Nobody was talking about the welds because nobody in procurement thought welds could be the problem. Steel is steel, right? Weld it according to spec. Inspect it. Stamp it approved. Ship it to Europe. The system worked. Except it didn't. And by the summer of 1944, replacement crews were arriving in Normandy, already knowing the Sherman's reputation. Some units were losing tanks faster than they could be replaced, not from German superiority in numbers, but from a joining method that should have been flagged as deficient 2 years earlier. The men doing the dying knew something was wrong with how these tanks were built. They just didn't know what, or that a welder in a Detroit shipyard was about to figure it out by breaking every rule in the book. The anti-tank terror. The 88, the gun that was turning Shermans into scrap metal, started its life as an anti-aircraft weapon. The 8.8mm Flak 18, developed by Krupp in the early 1930s, was designed to knock bombers out of the sky at high altitude. But German gunners in the Spanish Civil War discovered something interesting in 1937. Point that barrel horizontally at a Republican tank, and nothing survived. By the time Rommel's Africa Corps rolled into the desert in 1941, the 88 had been repurposed as the most feared anti-tank weapon of the war. The numbers tell you why. The standard 88mm anti-tank round, the Panzergranat 39, could penetrate 110 millimeters of armor plate at 1,000 meters. That's 4.3 inches of solid steel punched through like it wasn't there. The Sherman's front hull was 51 millimeters, sloped at 56 degrees, which gave it an effective thickness of about 90 millimeters against a direct hit. Do the math. The 88 could go through a Sherman's frontal armor from a mile away and still have energy left over to kill everyone inside. From the side, where the armor dropped to 38 millimeters, an 88 could penetrate from 2,000 yards out. That's over a mile. The Sherman crew wouldn't even hear the gunfire before their tank was burning. But penetration statistics don't capture the real terror of the 88. It was the gun's versatility and the way German crews employed it that made it a nightmare. The high muzzle velocity, 2,700 feet per second for armor-piercing rounds, meant a flat trajectory and minimal bullet drop. A competent gunner could put rounds on target at extreme range with frightening accuracy. American tankers in Tunisia reported taking fire from positions they couldn't even see. Watching as 88 rounds walked toward their formation, adjusting fire, then punching through tank after tank with methodical precision. The gun itself sat low to the ground when deployed, making it easy to conceal. German doctrine called for positioning 88s in ambush, camouflaged and dug in, waiting for Allied armor to roll into a kill zone. Once the shooting started, the 88's rate of fire, 15 to 20 rounds per minute with a trained crew, meant multiple tanks could be destroyed before anyone figured out where the fire was coming from. At the Battle of Fade Pass in February 1943, a handful of 88s destroyed 40 American tanks in less than an hour. At Villers-Bocage in June 1944, a single German unit knocked out 25 British tanks and 28 other vehicles in 15 minutes. The 88 was always part of those massacres, and here's what made it worse. The 88 could fire high explosive rounds at infantry and soft targets with devastating effect. One gun, two rolls, anti-tank and anti-personnel. A Sherman couldn't hide behind infantry support because the same gun that would kill the tank could also shred the supporting troops. American armor tactics relied on combined arms, tanks working with infantry. But the 88 made that doctrine suicidal at anything less than point-blank range. By mid-1944, American intelligence estimated Germany had over 10,000 88mm guns deployed on all fronts. Every tank crew heading into combat knew they'd face them. The penetration data was in the field manuals. Everyone understood that the Sherman was outgunned and under-armored. What they didn't understand yet was that even when the armor should have held, even when the angle should have deflected the round, those welds were giving out. The 88 was a terror weapon, yes, but the Sherman's construction was making it even deadlier than it needed to be. The unseen fix. Thomas Wilder wasn't supposed to be building tanks. He'd spent 12 years welding ship hulls at the River Rouge shipyard, joining plates on Great Lakes freighters, where a bad seam meant the whole vessel could crack apart in rough water. But in November 1943, the Army Air Forces canceled a major cargo ship contract, and Wilder found himself reassigned to the Chrysler Tank Arsenal in Warren, Michigan, one of 5 plants pumping out Sherman hulls for the final push into Europe. He was 52 years old, too old for the draft, with hands that could read metal through a welding rod. The kind of craftsman who could tell you if a joint would hold just by the sound the arc made and the color of the cooling bead. Shipyard welders lived by different rules than production line welders. On a ship, you welded for the worst conditions. Ice storms on Lake Superior, 30-foot swells, metal flexing and stressing for decades. You built joints that could take punishment. The military's welding specifications for tank armor looked wrong to him from day one. The Army called for a standard butt weld on the hull seams, a square groove joint where 2 plates met edge to edge, filled with weld metal flush to the surface. Clean, efficient, fast. The spec sheet, marked MEL STD 248, specified penetration depth at 75% of plate thickness, with the remaining 25% left as a backing. Made sense on paper. In practice, Wilder saw a problem. That remaining quarter-inch of unfused metal at the root of the joint created a stress concentrator, a weak point where the 2 plates weren't truly unified. On a ship, that joint would hold because the forces were distributed and mostly tensile. But a tank took impacts. High-velocity impacts from projectiles designed to find weak points. December 1943, Wilder got his proof. The arsenal maintained a small testing facility where they'd fire-captured German weapons at sample armor sections to validate the specifications. Workers weren't usually allowed near the range, but Wilder had befriended the sergeant running the tests, an older guy who appreciated that Wilder brought decent coffee from home. The sergeant let him watch a test firing. They'd mounted a section of welded hull armor, 2 plates joined exactly to spec, and put a German 75mm round into it at an angle, not even an 88, just the smaller 75mm from a Panzer IV. The weld split, not the plates the weld. The impact drove the joint open like someone had taken a chisel to it, and Wilder could see the unfused root gap right there in the failure zone. The shell hadn't fully penetrated, but it didn't need to. The separated seam would have let in enough thermal energy and fragmentation to cook off ammunition inside a real tank. The sergeant shrugged it off. The spec called for the joint to meet minimum standards, and it did, technically. But Wilder had seen enough failed welds to know this wasn't a fluke. This was structural. He went back to his station and pulled the MIL STD 248 specification sheet from the supervisor's office. He read it 3 times. The Army's welding engineers had optimized for production speed and X-ray inspection standards, not impact resistance. They'd never tested these joints against the kind of kinetic energy that an 88mm round delivered. And now those joints were in 50,000 tanks with more rolling off the line every day, heading straight into the teeth of German anti-tank guns that could exploit exactly this weakness. Wilder's solution was simple, which made it even more infuriating that nobody had tried it before. Instead of the standard square groove butt weld with 75% penetration, he'd use a double V groove joint with 100% penetration from both sides. Cut a beveled groove into each plate edge, weld from the outside, flip the section, grind out the root, and weld from the inside. Complete fusion. No gap, no stress concentrator. The 2 plates would essentially become one piece of metal at the seam. He knew the technique worked, because he'd been using variations of it on ship hulls for years. A proper double V joint done right created a weld stronger than the base metal. Under impact stress, the plate would fail before the seam would. That's what you wanted, but there was a problem. Actually, several problems, and they all pointed to the same conclusion. What Wilder was proposing was explicitly forbidden by military manufacturing specifications. First issue, time. A standard Sherman hull weld could be completed in 12 minutes by a competent welder following the spec. Wilder's method required roughly 35 minutes per seam, nearly 3 times as long. You had to bevel the plates, which meant extra machining. You had to weld both sides, which meant flipping heavy armor sections or accessing interior spaces that weren't designed for dual-side welding. You had to grind out the root pass, which added another labor step. In a production environment cranking out 16 Sherman hulls per day, that time penalty was unacceptable. The arsenal's production schedule was calculated down to the minute. Slow down welding by 23 minutes per seam and you'd cut daily output by 1/3. Second issue, X-ray inspection. The Army's quality control relied on radiographic testing that could spot voids and inclusions in the weld from one side. Wilder's double V joint was denser, with overlapping weld zones that could obscure defects in an X-ray image. The inspectors would have to shoot films from multiple angles, maybe even use ultrasonic testing, which meant more time and equipment that most facilities didn't have. MIL STD 248 explicitly stated that all welds must be inspectable via single-side radiography. Wilder's method failed that requirement by design. Third issue, and this was the big one, contractual liability. Chrysler had a binding agreement with the Army Ordnance Department to manufacture Sherman hulls according to approved specifications. Every weld was supposed to match the engineering drawings and spec sheets exactly. Deviation wasn't innovation. It was breach of contract. If Wilder modified the weld technique without authorization and a tank failed in combat, Chrysler could be held liable. Worse, if investigators determined that unauthorized welds contributed to casualties, criminal charges were possible. The War Production Board didn't mess around with contractors who went off script, especially when lives were at stake. Wilder understood all of this. He also understood that men were burning to death in tanks with legal, specification-compliant welds that split under impact. So in January 1944, on his own initiative, during a night shift when the supervisors were thinner on the ground, he took a scrap section of hull plate and welded it his way. Complete penetration, double V groove, the works. Then he found the sergeant at the test range again and asked for a favor. "Fire something at this piece, would you? And let's see what happens." The sergeant told him he was crazy. This wasn't authorized. If anyone found out, Wilder would be fired at minimum, possibly prosecuted for sabotage or interference with military production. Wilder handed him the coffee thermos and said, "Test it anyway." They mounted Wilder's test piece on the range at 200 hours on a Friday morning in late January. The sergeant had access to a captured German 88mm round, just one, pulled from a dud that British demolition teams had recovered in Italy. He loaded it into a test fixture designed to simulate battlefield impact angles, set the target at a realistic engagement distance, and fired. The sound echoed across the empty facility like thunder. The plate held. More than held. It barely deformed. The 88mm round hit the welded seam at a 30-degree angle, exactly the kind of oblique impact that had been splitting standard Sherman welds open in North Africa. The shell gouged a crater into the armor but didn't penetrate. And more importantly, the weld seam stayed intact. No separation, no crack propagation. The two plates remained unified. Wilder ran his fingers along the backside of the impact zone and felt the metal's memory of stress. But the joint itself was solid. The metallurgy behind why it worked comes down to how metal behaves under sudden, violent stress. When you weld two pieces of steel together, you're not just melting them, you're changing their molecular structure in three distinct zones. There's the weld metal itself, the molten material you've added. There's the fusion zone where the base metal actually melted and mixed with the weld metal. And then there's the heat-affected zone, or HAZ, where the base metal didn't melt but got hot enough that its grain structure changed. That HAZ is critical because it's often the weakest part of the whole assembly. In the Army's standard 75% penetration weld, you had a large HAZ on the outer surface where the welding was done, but the inner 25% of the plate, the root, never got hot enough to truly fuse. It was just sitting there, held in place by the mechanical constraint of the weld above it. Under normal stress, fine. Under high-velocity impact, that unfused root became a crack initiation site. The shock wave from an 88mm round would propagate through the armor plate, hit that discontinuity, and the joint would unzip like a zipper. Basic fracture mechanics. Wilder's double V joint eliminated the discontinuity by welding from both sides with complete penetration. He created a continuous fusion zone through the entire thickness of the plate. The grain structure in the HAZ was smaller and more uniform because the thermal cycle was controlled. You weren't trying to drive heat all the way through from one side, which would overheat the surface and underheat the root. Instead, you were heating each side appropriately, creating a symmetrical metallurgical bond. When an impact hit, the stress distributed evenly through the joint because there was no weak spot for cracks to exploit. There's another factor: residual stress. Standard butt welds create asymmetric cooling patterns that leave the joint in tension on one side, which makes it more susceptible to brittle failure under impact. The double V joint's symmetric heating and cooling reduced residual stress significantly. The weld was in a more balanced state, more ductile, better able to absorb energy rather than fracture. The sergeant looked at the test plate, looked at Wilder, and said they needed to run this again with proper documentation. Wilder shook his head. Documentation meant involving people who'd shut the whole thing down before it got anywhere. What they needed was someone in the field, someone who understood that survival mattered more than production schedules, someone willing to try unauthorized welds if it meant crews came home alive. Breaking the chain, getting the technique to Europe required breaking the chain of command. Wilder couldn't go through Chrysler management. They'd kill the idea to protect their contract. He couldn't go through the ordnance department. They'd cite regulations and liability. So he went sideways, through a network that existed outside official channels, the men who actually fixed tanks in the field. Legacy: the War Department never officially acknowledged the modification. They couldn't, because that would mean admitting the original specifications were deficient, which would open them to legal and political consequences. But the data was undeniable, and the men doing the fighting had voted with their lives. Thomas Wilder never received a medal, never got a commendation letter, never saw his name in any official report about improved Sherman survivability. He retired from Chrysler in 1949 with a pension and a handshake. Just another factory worker who'd done his part for the war effort. The men who actually knew what he'd done, Chen, Kowalski, the maintenance crews who'd spread his technique across Europe, they knew. But the official record stayed silent because acknowledging Wilder meant acknowledging that the Army specifications had been killing people. The specifications changed anyway, just quietly. In 1946, the Army Ordnance Department issued revised welding standards for armored vehicle construction under MEL STD 1261. The new specifications called for full penetration welds on all primary structural joints with mandatory dual-side inspection and modified groove geometries that looked suspiciously like Wilder's double V joints. The revision notice didn't mention combat experience or field modifications. It was presented as routine improvement based on additional metallurgical research. Nobody who'd been in Europe was fooled. The real validation came during the Korean War. The M46 Patton tank rushed into service in 1950 used full penetration, Welding on all hull seams is standard production procedure. When those tanks started taking hits from Soviet-supplied T-34-85s and anti-tank guns, the welds held. After-action reports from the 1st Marine Division noted that patents could sustain multiple non-penetrating hits without catastrophic structural failure, exactly what the modified Shermans had demonstrated in France. The difference was that now it was designed in from the start, not jury-rigged in a field maintenance depot. By the 1960s, Wilder's principle had become foundational to armor welding worldwide. The M60 patent incorporated advanced welding techniques that ensured complete fusion through the entire armor thickness. Soviet tank designers adopted similar methods for the T-62 and T-72. The British Chieftain, the German Leopard 1. Every major tank design from the Cold War forward treated weld integrity as non-negotiable. The joints had to be stronger than the plates, no exceptions. Modern tank construction goes even further. The M1 Abrams uses a combination of advanced welding techniques and modular armor arrays, but the underlying principle remains. The seams are never the weak point. Welding procedures for the Abrams hull require multi-pass techniques, post-weld heat treatment, and ultrasonic inspection that would have seemed like science fiction in 1944. But the core concept, complete penetration, symmetric fusion, elimination of stress concentrators, that's all Wilder, refined and perfected with 70 years of metallurgical advancement. The lesson extended beyond tanks. Armored personnel carriers, naval vessels, pressure hulls for submarines, even civilian applications like petroleum storage tanks and high-pressure pipelines. All of them use welding specifications that trace their lineage back to the principle that a craftsman in Detroit figured out by trusting his hands and his experience over a specification sheet. The American Welding Society's D1.1 Structural Welding Code, the international standard for critical weld joints, incorporates full penetration requirements for high-stress applications. Wilder never contributed to that standard, but his work is embedded in it. There's a broader truth here about how innovation actually happens during war. It's not always engineers at proving grounds or scientists in laboratories. Sometimes it's a 52-year-old welder who knows how metal behaves, who sees a problem everyone else is ignoring, and who's willing to break the rules because he understands that saving lives matters more than following procedures. Wilder's illegal welds kept enough crews alive that the technique couldn't be suppressed, only eventually adopted. That's how change happens when bureaucracy meets battlefield reality. Slowly, grudgingly, and without ever quite admitting it was necessary. Legacy: the War Department never officially acknowledged the modification. They couldn't, because that would mean admitting the original specifications were deficient, which would open them to legal and political consequences. But the data was undeniable, and the men doing the fighting had voted with their lives. Thomas Wilder never received a medal, never got a commendation letter, never saw his name in any official report about improved Sherman survivability. He retired from Chrysler in 1949 with a pension and a handshake. Just another factory worker who'd done his part for the war effort. The men who actually knew what he'd done, Chen, Kowalski, the maintenance crews who'd spread his technique across Europe, they knew. But the official record stayed silent because acknowledging Wilder meant acknowledging that the Army specifications had been killing people. The specifications changed anyway, just quietly. In 1946, the Army Ordnance Department issued revised welding standards for armored vehicle construction under MEL STD 1261. The new specifications called for full penetration welds on all primary structural joints with mandatory dual-side inspection and modified groove geometries that looked suspiciously like Wilder's double V joints. The revision notice didn't mention combat experience or field modifications. It was presented as routine improvement based on additional metallurgical research. Nobody who'd been in Europe was fooled. The real validation came during the Korean War. The M46 patent tank rushed into service in 1950 used full penetration welding on all hull seams as standard production procedure. When those tanks started taking hits from Soviet-supplied T-34-85s and anti-tank guns, the welds held. After-action reports from the 1st Marine Division noted that patents could sustain multiple non-penetrating hits without catastrophic structural failure, exactly what the modified Shermans had demonstrated in France. The difference was that now it was designed in from the start, not jury-rigged in a field maintenance depot. By the 1960s, Wilder's principle had become foundational to armor welding worldwide. The M60 patent incorporated advanced welding techniques that ensured complete fusion through the entire armor thickness. Soviet tank designers adopted similar methods for the T-62 and T-72. The British Chieftain, the German Leopard 1. Every major tank design from the Cold War forward treated weld integrity as non-negotiable. The joints had to be stronger than the plates, no exceptions. Modern tank construction goes even further. The M1 Abrams uses a combination of advanced welding techniques and modular armor arrays, but the underlying principle remains. The seams are never the weak point. Welding procedures for the Abrams hull require multi-pass techniques, post-weld heat treatment, and ultrasonic inspection that would have seemed like science fiction in 1944. But the core concept, complete penetration, symmetric fusion, elimination of stress concentrators, that's all Wilder, refined and perfected with 70 years of metallurgical advancement. The lesson extended beyond tanks. Armored personnel carriers, naval vessels, pressure hulls for submarines, even civilian applications like petroleum storage tanks and high-pressure pipelines. All of them use welding specifications that trace their lineage back to the principle that a craftsman in Detroit figured out by trusting his hands and his experience over a specification sheet. The American Welding Society's D1.1 Structural Welding Code, the international standard for critical weld joints, incorporates full penetration requirements for high-stress applications. Wilder never contributed to that standard, but his work is embedded in it. There's a broader truth here about how innovation actually happens during war. It's not always engineers at proving grounds or scientists in laboratories. Sometimes it's a 52-year-old welder who knows how metal behaves, who sees a problem everyone else is ignoring, and who's willing to break the rules because he understands that saving lives matters more than following procedures. Wilder's illegal welds kept enough crews alive that the technique couldn't be suppressed, only eventually adopted. That's how change happens when bureaucracy meets battlefield reality. Slowly, grudgingly, and without ever quite admitting it was necessary.